so it's my great pleasure to now introduce Christoph Sunderhauf, a senior quantum scientist at Riverlane, which is a quantum computing company, actually established here in Cambridge 8 years ago. So today, Christoph will tell us about quantum algorithms, data inputs, and loading challenges. Please.
Thank you very much for the introduction and for giving me the opportunity to speak here. Yes, so I'm talking about data loading, data input in quantum computing, which sounds like a very broad topic. And to be more specific, I will be talking about block encodings, which are one model of inputting data. And specifically, if you want to input matrices that have some kind of structure into your quantum computer. So that's the article that the talk is based on. The title contains a lot of words, and I'm going to start explaining block encoding because I don't think everybody is familiar with that. The block encoding is a popular way to input matrices into quantum computers. So the matrix A that you're interested in, it might not even be unitary, so you can't just like implement it with quantum gates. But what you can do is you can input it as a block of a larger unitary U. So here, what the junk exactly is doesn't matter. The junk blocks, they just ensure that the big unitary U is unitary, and then you can implement that with gates on your quantum computer. Furthermore, there you see this 1 over alpha, which is the subnormalization. And you might need a subnormalization just on normalization grounds for this even to exist. Because in the unitary, of course, each of the rows are normalized vectors. And if the A is too large, then it would be impossible to find junk. There's another way to think about this related to quantum circuits, which I want to show you because that's how I think about them. Which is, so assuming for now that the junk has the same dimension as the A, then you can write this thing as a tensor product just by using the computational basis vectors, where the 0, 0 gives you the top left entry here. And then if you decompose this as a tensor product, you can write this thing as a quantum circuit. So I've split this into two registers corresponding to the first and the second component of the tensor product. And now what you see is if you initialize the first register as 0, which I call the flag qubits because they flag their matrix inside the block encoding. If you initialize them as 0 and you also post-select them as 0, so this means you either measure and repeat the whole thing until you get to 0, or you project the whole thing onto 0, then you recover your matrix on the bottom. So you see this from this tensor product structure because what the initialization and post-selection of the flag qubits does it is selects your first part here of the tensor product decomposition, the first summand. Okay, so this allows you access to your matrix. And this is one nice way to think about block encodings. But why should you care about these block encodings at all? And the reason is because they are a popular input model and occur in many, many different quantum algorithms. I'm just going to give you a few references here that are like a start for a treasure hunt if you're interested. So first I want to mention the quantum singular value transformation. There was actually a paper called Grand Unification of Quantum Algorithms, which used the quantum singular value transformation and showed that most known quantum algorithms can be written using QSVT. And it uses block encoding, so it's fundamental input and output model. Then Hamiltonian simulation, we already heard about this this morning a bit. You can do Hamiltonian simulation also using block encodings if you create a block encoding of your Hamiltonian. You also, if you look at literature on quantum chemistry, you will read a lot about qubitization and phase estimation, which also use block encodings of the Hamiltonian in order to find your ground state energy or to do something else what you want to do. And in all these cases, it's important to have an efficient block encoding, which means that the alpha is small and you have few gates in the U, but I will get to that in a moment. First, something else which is maybe a bit unexpected, so unexpected that I kind of forget it, is you might think of a completely different model, which is like adiabatic quantum computing. And so this is where you like slowly change the Hamiltonian of your machine in order to go from an easy state to a difficult state. And you can actually also do this digitally in the circuit model. And then there are also algorithms that use block encodings as an input model for these algorithms. But my favorite quantum algorithm is the quantum singular value transformation, So I want to explain it a bit to you. So what the quantum singular value transformation does is allows you to apply a polynomial to a matrix, which is given in a blocking code. And the circuit, so this is a circuit here for a degree 3 polynomial, because it has like 3 iterations. For a higher degree polynomial, it would just be more iterations. And what I like is that the circuit structure is super simple, and it just has these 2 different elements which are distinct from each other. You have in yellow the blocking coding, which describes the matrix you want to apply the polynomial to. And then you have in green these rotation angles, which are the phase factors, and they describe which polynomial is going to be applied to the matrix. And these are separate, that's the nice thing. You can use the same phase factors with a different blocking coding for a different matrix. Or you can, if you have your matrix and you want to apply a different polynomial, you just need to use different phase factors, but you can use the very same circuit template. And here the top 2 qubits are flag qubits, the top 2 registers, and at the bottom they allows you access to your output matrix. This sounds maybe a bit abstract, applying polynomials to matrices. Is there like any real world value to this, or why would you even want to do that? And the answer is because you can approximate many functions by polynomials. Basically all of them, it just depends on how well you can approximate them and how high your degree has to be. So for example, if you're looking at matrix inversion, which might be useful in solving differential equations on quantum computers, then what you kind of want to do is you want to execute 1 over x, which is the black dotted line here. And then you can approximate this with a polynomial, which is the blue one. And if this line kappa, if it moves further to the left, which means the matrix becomes more difficult to invert because the condition number becomes smaller, becomes larger, then your polynomial here, the blue line, needs a higher degree, and you need longer circuits. I want to go back onto what the QSVT does, like on this blocking coding level. So you start with this input blocking coding, U, of A over alpha. And then the QSVT gives you a second blocking coding of the P of A over alpha. And the junk here actually is bigger, so the blocks, the output junk blocks have a bigger dimension than the input junk blocks. Because we have this additional flag qubit here, so they're like double the size of the initial junk blocks. But what the content is doesn't matter at all, because you just initialize the flag qubits as 0 and post-select them as 0, and you get out your P of A over alpha. And now when you read about what is the complexity of doing this matrix inversion with QSVT, what you will read is that the degree of the polynomial you need goes like kappa log kappa over epsilon, where kappa is a property of the matrix, the condition number, and epsilon is the accuracy you desire. And I already told you that if you have d queries to u, then that's the length of the circuit. You have d of these iterations. So this here, the kappa log kappa over epsilon, this is the query complexity of matrix inversion with QSVT. But now, if you actually want to invert a matrix, and you actually want to ask, how long will this computation take on my quantum computer? And it's not the query complexity that you're interested in, it's the gate complexity. Because it will also take you some gates to implement your blocking coding U. And yeah, that's then on the bottom, the gate complexity. And this is why I think for practical applications, or also theoretically, if you're just assessing, will there be like a practical quantum speedup, it is super important to look into the implementations of these oracles, like the blocking coding U here, and finding how can I make an efficient circuit for this blocking coding there. And not just have it like a black box inside the query complexity, so to go even beyond that. In fact, I brought this meme here, which I made, which likens a quantum speedup to an ancient Greek superhero, Achilles, who is super powerful. But you all know Achilles has a weakness, which in this case is when he encounters real-world applications, which come with some real-world data that you get maybe from your project partners that you're working with on your grant. And then they want to invert those matrices, and then, okay, how do I put them to the quantum computer efficiently? And that's how you can shoot Achilles into the foot and annihilate any quantum speedup if you're unlucky with the data loading. If you're lucky and you found a way to load your data efficiently, you've got another chance. because in the end you want to read everything out. And if there is no cleverer way to do this, but you need to do full state homography, then that again is exponentially expensive in your number of qubits, and any quantum speedup is gone. Any exponential quantum speedup is gone. So maybe you're thinking this problem of data loading as somehow related only to these block encodings, because I've talked about it in that context. But I want to convince you that this data loading and data input is a general bottleneck that you will find everywhere in quantum algorithms. And in order to do that, I want to talk about Grover algorithm, which I think everybody will have heard of. The Grover algorithm is often described as a quantum algorithm to do unstructured search in a database of size n in time O of square root n. This gives you a square root speedup because classically you would go like through the list like one by one in time n. So it allows you to find the needle here in a haystack. And here the circuit, I've just copied it from Wikipedia. And for sure you can see that you have this repetition of square root of n times here, which is your length of the circuit and gives you the square root. But then if you look closely at the circuit, there is this u omega, and that's the haystack. This is an oracle which somehow gives you access to the entire haystack, your entire database. And now, if this oracle here, if it loads just your classical unstructured list with O of n gates because it has n entries, well, then you can multiply the n and the square root of n together, and you get a quantum slowdown. So this example illustrates that looking into the oracle can be important, and especially data loading, because here it's the loading of the list into memory, can be a huge bottleneck, and you need to be very careful about this when constructing quantum algorithms. I would say in every context, for every quantum algorithm. So this brings me back to the block encodings. How do we construct an efficient block encoding circuit? And let me take a step back here and first ask, what does it mean to have an efficient block encoding circuit? So the first thing is pretty self-explanatory. You want few gates in your block encoding. Specifically, I will focus on T gates, which are a gate which are more expensive than Clifford gates in many fault-tolerant quantum computing paradigms. And then the second thing, which is less obvious, is that you want a small subnormalization alpha. So that was the scaling factor that it is divided by. But you can think of it as this way: if your alpha is super gigantic, then your entries in the matrix will be very close to 0 because you have A over alpha. And then you will have very little signal in your matrix, and that can't be good if you have very little signal. Then also the qubit count should also be, that would be nice if it was also good. And now what this work here is about is that if we have a matrix which has some kind of structure, and you will learn more about what this exactly means on the next slide, specifically in the sparsity pattern. So if we have a pattern of non-zero elements, and most elements are 0. This can often happen if you have, for example, some kind of locality structure, like in some kind of mesh, it's only the nearest neighbors or next nearest neighbors which are talking to each other. So there's two kinds of structure I consider here, which is the sparsity pattern, and then also repeated elements. Because in your pattern, in your sparsity pattern for your matrix, you might have a pattern of the same number being repeated many times. And then with this method, you can only load this number once effectively, and thereby reduce the data loading cost. And we also avoid loading the zeros explicitly for the sparsity pattern. Okay, so how does this work? I've brought you an example matrix here, which is just an example. You can do this for many other matrices, which is a Toeplitz matrix. So it has capital D different values, and they're organized here in such a way that on these D diagonals, like each diagonal has the same value, so it has lots of repetitions, and also zeros here in the corners, a lot of zeros. And now what you need to do is you can label these elements in 3 distinct ways. So there's 3 ways to think about this matrix. So you label like all of the positions of the non-zero elements. You label all of these positions in 3 different ways. The first one is by column. So you can take the column index j, And then you can find this position by counting down by the sparsity index for like it's the S non-zero element in this column. So like, I don't know, what, 0, 1, 2, 3, 4, 5th, maybe that's the 5th non-zero element in that column. Equivalent, you can address the same position by row. You can start with the row index I, and then count how many non-zero elements are there, and what number is it, what's the S, the sparsity index corresponding. So capital S is here the maximum number of non-zero elements per row or per column. And now the third one is by repeated values. So you have this data index lowercase d, which enumerates the different values, the different numbers that occur in your matrix. In this case, that corresponds to one of these diagonals. But if you have another structure, it could be very different. And then your M is a multiplicity index. And similar to the sparsity index, it counts like which of these elements of that value, which of these positions do I actually mean. Now, these are three different ways to locate the same position in your matrix. And what my blocking coding circuit is based on is oracles that translate between these positions. So this is just what I'm going to call them. N for the dimension of the matrix, S the sparsity, D the number of data items, number of distinct data items, and M the multiplicity, so how often it can occur. And we have this kind of equation here, and S equals dm, which counts the number of non-zero elements in the matrix from two different perspectives. So the left-hand side is the number of rows times the number of elements per row. And the right-hand side is the number of distinct elements times the multiplicity of each. And now this is the assumption on the structure that the matrix has to have. The assumption is that we can somehow arithmetically translate between these different labelings. So we can somehow find arithmetic expressions to go from the column to the repeated value description. Because the matrix is structured. This is what I mean by structured. And if you have some arithmetic expressions to translate them, to go from one labeling to the other one, we can translate that to quantum arithmetics. Because there's circuits for like quantum addition and quantum multiplication and things like that. So we can create arithmetic circuits that translate between these labelings. And that's the basis of the block encoding. Okay, this page is maybe a lot right now, but I'm going to walk you through all the elements of the circuit. So this is the block encoding circuit that we can use to input the structured matrix and harnessing the structure. And the top three registers here are flag qubits. And at the bottom, you will have access to your matrix that you're trying to block encode. And these are the oracles that are made of these arithmetic circuits that translate between labelings. I've color-coded it here kind of, so you can see that it goes from a column description, which also matches the input index that you have, the J, then over to repeated value description and back to column description. You might notice that this here is a different color than the registers out here. And the reason is because the registers can have a different dimension. So on the outside, they have the dimension of, well, n, because that's for the J register, and the sparsity, and the inside they have for repeated elements and multiplicity. But because of this equality, ns equals dm, the dimensions match up, and these OR and OC oracles, they can be unitary. Because the dimensions also match up. The thing in the middle is the actual data loading. And what I mean by this slash notation with the slash control is that it's a multiplexed gate. So we perform a rotation on the data qubit with a different rotation angle for each value here of d. So depending which computational basis state this register is, we perform a different rotation. And the H's, some people call them diffusion operators, so they create an equal superposition state. You'll see that on the next slide. There's also the possibility to add an out-of-range oracle here if you have a matrix which is not quite according to the pattern, but you have to like zero out some elements. So for example, maybe you have a very structured matrix, but then you have some boundary conditions, which causes some elements to be zero, like outside of your structure, and then you can use this to zero them out. Okay, so how do I think about this circuit? Let me start again with what a block encoding circuit should do. So it should give you access to the matrix divided by the subnormalization if you initialize and post-select correctly. And so this is what we're going to do to understand the big circuit now. I've just put the 0 input and the projection at the very end here. And now I've just moved it onto the individual registers. Okay, the next thing we can do is we can apply these diffusion operators, the H's. So they create these equal superposition states over the capital S basis states. That's why we get this normalization of 1 over square root of S. And in the simplest case, if your S is a power of 2, it's just Hadamard's on all of the qubits in that register, and then you get this equal superposition state. Okay, and now the next thing is to look at what these oracles here do. So what we have here on the left side is we have an equal superposition over all elements in column J. Because we have the J, and then we have the equal superposition over all S. And this corresponds to equal superposition over all labels of all the elements in column J. And now we just translate these into this other labeling. So this means what we get is we get an equal superposition again over all elements in column J, just with the other labeling, because we have translated them from the JS to the DM labeling. So the same thing happens on the right. Here what I've written on the right is I have an equal superposition over all labels for the non-zero positions in row I. And that's the same what I have here. I have my index ix fixed because that's my output onto which I project for which element I want to access. And here on the right side I have an equal superposition over all positions in row I. And this 1 over f at the beginning was just I combined these 1 over square root of s prefactors from both sides. Okay, the next thing is going to be this rotation here. So I never told you exactly what the rotation is. It's an x rotation by 2r cosine of an AD, which is the matrix element, the value, divided by the maximum element in the matrix. And the reason there is this 2 and the r cosine is because then when you perform the rotation, the 2 and the r cosine disappears. I always get confused about this factor of 2, but that's just in the definition of the rotations and because of how the block sphere works. But basically, if you perform this rotation onto the 0 qubit, you see that for the 0 state, you already get exactly what you want, which is your matrix element. And the 1 part gets annihilated because we are projecting onto the 0 state. So I just get this prefactor, another prefactor. And now I'm basically done, because you can contract these two at the bottom. So the control here, to control which D you're accessing, doesn't change like the D index, it's just a control. So this means the D and the M, like on the left and on the right side, they must be the same. So initially I had some primes on the right side, but they're the same, of course. Otherwise, we could just get 0. So this means that if I contract this entire circuit, I just get AD over SA max. I just accumulate all of the factors everywhere. And the interesting question now is which AD do I get? Which value do I get? And you get the 1, which is the D for the D in column J. That comes from the left side of the circuit here. But you also get it for the D in row I, from the right side of the circuit. So you get it for that D, for that element, which is both in column I and both in column J and in row I, which is precisely the matrix element at this position, at this location, Aij. From here, we can also read off the subnormalization, which is the denominator, this S times A max. And the advantage here is, of this method, is that when you perform this control with the controlled rotations, you only control it on the register of size capital D for the actual distinct data elements, because that's like the expensive part. And that's how you can save, because you harness the structure and only perform one rotation for each repeated value, and not if there's like multiple repetitions. You don't perform a rotation for each of the repeated same values. Okay, and then you can add this out of range oracle. But, yeah. Okay, and this was the subnormalization. Okay, now let me take a step back and go a bit beyond just this exact circuit implementation. So even if you didn't follow that, this is a good time to step in again. Which is I have several contradicting maybe things here. I want few gates, but I also want a small subnormalization, and I want few qubits. So there must be some kind of trade-off that I make. Like often you can do a space-time trade-off, like you can use more gates and fewer qubits, or the other way around. And I'm not going to talk about that. But what is the link between the first two ones, the subnormalization and the number of gates? And to understand that better, I want to talk a bit about amplitude amplification. So amplitude amplification is a generalization of Grover's algorithm. And you can do it in QSVT with a polynomial. And what it allows you is it allows you to amplify block encodings in this way. To basically multiply your block encoded matrix A over alpha by some amplification factor gamma. And it is because of this amplitude amplification that this is the figure of merit you should be considering for block encodings, which is the number of gates times the subnormalization. And this is because this figure of merit stays invariant under amplitude amplification. So the cost of doing this QSVT, so the degree of the polynomial is approximately linear in gamma. These deltas and epsilon are like different precisions and accuracies controlling the amplitude amplification, but mainly it's linear in gamma. And so we see if we do perform amplitude amplification by gamma, the t cost of the block encoding goes up by gamma. But what happens to the subnormalization is the subnormalization goes down by gamma. Yeah, so I've put them here in the figure of merit, and then they cancel out, and my figure of merit stays the same. And so this shows that when you're considering this trade-off between subnormalization and number of gates, this is the correct figure of merit because you can always do amplitude amplification. In fact, you should, because if you scale this up, if you reduce the alpha, it increases your post-selection probability. So where I said at the end, when you measure the flag qubits, you have to hope that they're all 0, or else just repeat everything again. And the probability for measuring them in all 0 increases as you do amplitude amplification. And in fact, you get the square root Grover speed up. So doing the amplitude amplification is like square root more favorable to doing the post-selection with just repeat until success. What is the cost of the block encoding circuit? So this is the last technical slide. And we already have the subnormalization, which was just the denominator from the previous slide, which was the sparsity times the maximal element. And here we can look at the different circuit elements. So these diffusion operators on the very outside, if the S is a power of 2, you just use a bunch of Hadamards, and that's 0 T gates. But even if the S is not a power of 2, you can find efficient circuits for that. And then comes the big assumption, which is that we have this arithmetic structure, and that you can describe these conversions between the different labelings with arithmetic circuits. And arithmetic quantum circuits you can implement in polylog n time, so with polylog n gates. But this is like the big assumption here. Then I'm also assuming that you only have a small constant number of elements that you need to delete with this out-of-range oracle. And then here in the middle, this is the data loading cost. And if you use something like a unary iteration circuit or a general multiplexed rotation gadget, so a way to implement rotations controlled in different ways, that give you different rotation angles depending on what the D register is, the cost will scale like capital D, because that's the number of different rotations that you have to do. That's where the saving here comes in. And I think in general, usually, I guess the D will be the dominant part. So in the example I showed you with the tuplets matrix, the D might actually be just constant as you increase the size of the matrix, depending on what you're doing. And then these log n's will be dominant, or where the polylog n's. But in many applications that I've seen, actually your D will be the dominant one. So that's why for putting the figure of merit, I have just used the D as a drop-in for the circuit length. And then you get this figure of merit d times s times A max. For more information, you can scan this QR code, which links to the paper, where we show two further schemes that can improve the subnormalization of the block encoding even further, so do an even better block encoding. Then in many contexts also, you want a block encoding circuit which is Hermitian, because, for example, that allows you to do qubitization. And it also has a section where it shows how you can achieve that, often without any extra cost. There's also a number of examples where I've worked out how you would actually implement these oracles that translate between the different labelings, or how to implement this data loading part and so on, with these multiplex rotations that show this in more detail down to the quantum gates. And then finally, there's also an appendix on the singular value amplification. So I didn't invent the singular value amplification, of course, but in this appendix, I was trying to figure out more about the prefactor. So I said it's almost linear in gamma, O of gamma, but I was curious, what is the prefactor? And it turns out the prefactor is around 3. Finally, I want to go back to ancient Greece. And this is a picture here of the Oracle of Delphi. And I hope what I've inspired you today is that it's important to look towards the horizon and beyond the oracles, and look more closely at all of these blocks here and what the blocks are made of, and how expensive is it to actually implement these blocks, because for any practical applications, or also just in assessing whether there might be some quantum speedup for a problem, the implementation of the oracles can be very important, and especially data loading seems to be an issue which can pop up everywhere in many different contexts. Thank you.
Thank you very much. Do we have any questions to Christoph?
Thank you for the talk. I was wondering if, say I had a matrix which didn't quite have this nice structure, but was kind of close to it, like, say, within, like, Frobenius norm epsilon or something along those lines. Are there ways in which you can adapt these techniques to those kind of matrices, kind of approximate matrices?
So if it's very close to the approximate matrix, if it's very close to the other matrix in, I would say, in not like, so if it's the same in values, but like not in structure, so that some elements are off, like maybe because some elements are 0 or a few elements, a small handful of elements are different, then you can still use the same matrix and just explicitly add in the rotations to change the values of those few elements. And if it's only a handful or a constant number of elements, it won't change your circuit. It won't change the cost asymptotically or dramatically or anything. So that's one thing you want to do. If you have values that are very close to each other, you could do something like approximate your matrix by just setting them all to be equal. But that will, of course, incur you an error in your matrix. And yeah, so in general, I think it will be good to also approximate your data. And you can use many different methods. We actually did something recently for approximate state preparation, where you approximate your data together with Oliver, who is sitting there in the back. But this one is really about, you can do it exactly, if your matrix has the structure exactly. But you can combine it with, I think, with different ways to approximate your matrix. Yeah.
So I'm really strongly in favor of this approach of taking structure of a particular kind of data set and doing something very efficient just for that case. Do you have any other classes of matrices in mind apart from template space?
Yes. So I think one advantage of this method is also that for each class of structure, you only need to do like the hard part once, like figuring out what these OC and ORs are and what these, how you translate between the labelings. And then when you have that, you can use it. You have like a template circuit, and you can change the data easily just by changing the values here in the rotations. Okay, so other class of circuit that I've looked at was like a discrete other classes of structured matrices that I've looked at, where like a discrete Laplacian for example, for a 2D grid. Or also a binary tree matrix, which encodes a binary tree, where there's repetitions in the values on the nodes or on the leaves. Yeah, and originally, it came from a matrix. So I got this idea because in a collaboration with Rolls-Royce, we were looking at a matrix which was used in an algorithm to solve some computational fluid dynamics problem, which had not that many repetitions, but a few repetitions, also because of the two-dimensional structure of the toy problem we were considering.
Just one last quick question.
Is it possible that the structures you're identifying should make it easy to design a block encoding would also make the matrices easy to process classically?
That's a very good question. And in fact, they do. So if you want to invert a sparse matrix classically, you wouldn't just use like a classical inverter for a dense matrix, but there are algorithms that allow you to, that are like specifically tuned for sparse matrices. They also usually, where was it? Here. Here they also scale with this kappa, which is the condition number of the matrix, these classical algorithms, and they scale with the sparsity, like the block encoding. Yeah, I think in general, maybe if you study your matrix very, very well, you can find a classical algorithm. I don't know, I'm not an expert in that area. But yeah, I guess, yes, you should. I guess there's also a general problem in quantum algorithms that you always have to pit it like against the best classical algorithm, which is not necessarily like the general one, but it might be a super specialized one, which is like super specialized for your specific use case.
Thank you very much. So I suggest we thank Chris again.